Welcome back to the classroom. My name is Mr. Wong, and today we'll be looking at the 2019 Independent Physics paper, question 29. This is going to look at Module 6, Inquiry question number 1, which is how charged particles behave in electric fields and magnetic fields. So let's get started and look at how to approach this question. We have a scientist who's fired a beam of charged particles into a magnetic field strength of 0.8 Teslas. So let's just highlight some of that information. And it's moving at that particular velocity. They measure the radius of the curvature to be 0.15 meters. Okay. So the scientists concluded that the beam was composed of electrons. Using the data given, evaluate your conclusion. Okay, well, there's probably two ways we can think about this. One of the features of an electron is it is a negative charge. And we also know as a value, the charge is negative 1.602 times 10 to the power of negative 19 coulombs. So we want to demonstrate that it's negative and the charge is that particular value. The first way we can demonstrate that is by using the right-hand palm rule. Okay, if you recall, using our right-hand palm rule, our fingers, okay, I'll just draw our fingers out here. The thumb is the direction of, your right thumb is the direction of the positive charge. Your fingers is the direction of the magnetic field. And the palm of your hand is the direction of the force applied onto the charged particle. So let's try and highlight this out. So in terms of the direction, the magnetic field is coming into the page. Remember, the crosses represent into the page magnetic fields. The direction of the charge, we can work that out later in terms of if it's positive or negative. The direction of the force applied is, in this case, down initially. Okay, and then obviously it kind of goes in a circular motion going in. So if we're using our right hand palm rule, my fingers are pointing into the page and my palm is pushing down, right? So look at where your right thumb is directed. Now, if you've stationed your right thumb correctly, your right thumb should be positioned to move towards the left-hand side. Okay, now remember, positive and negative charges always move in the opposing directions of each other. So in that case, this motion that I have here is the negative charge. Okay, so using the right-hand palm rule, I've proven that the motion of this particular charge particle could only occur if it's a negative charge. So there's that. Now, another thing we can look at is, given the data provided, calculate or evaluate the conclusion provided. So what else can we look at? We have magnetic field strength, we have velocity, and we also have the curvature of the beam at that particular point. So we know in this point in time, so using the right-hand palm rule, the particle is negatively charged. And what we talked about before, so the magnetic field strength and the centripetal force are equal to each other. What that leads to is the following equation: QVB equals to mv squared over r. If we rearrange the equation to make it a charge to mass ratio equivalent, it becomes v over RB, and we said that that value was about 250,000 coulombs per kilogram. If we then want to find the mass of the object, okay, so we know that the fundamental charge is this value here, so we can do 0.602 times 10 to the power negative 19 m equals to this value here. Okay, and we get a value of m which is equal to 6.408 times 10 to the power negative 26 kg, which is not equal to the mass of an electron, which is 9.11 minus 31, that. Okay, so what we can say is it does not have the same mass as an electron, hence scientists have the wrong conclusion. And that's how you would solve for question A. Okay, so just remember we did assume that they were electrons, hence we used the value of 1.602 times 10 to the power 19. And if indeed we did get electrons, the mass expected should have been this value here, which we didn't. Therefore, we know it's negatively charged, but it's not an electron because it doesn't have the same mass. Okay, wrong conclusion, not the same mass. Could use with a couple more lines, I must say, for this question, but that'll do. Question B, on the diagram above, show the path the beam of the charged particles would take as it left the magnetic field. Okay, so in order to do that, I'll probably have to just rub out this bit here because it gives a nice little explanation. Okay, so what actually happens is you can see as the charge goes out, so this is where it exits. As it exits, there is no more force being applied onto the charged particle. So according to Newton's first law, whatever motion it was partaking in originally, that's the motion that it will have. So if we look at this here, the vectors are, it's still moving forwards or moving towards the right, and it's moving down like that. So if in the chance where there's no more force applied, both the horizontal component and the vertical component are applying, or the components are at a constant speed, then we get a linear motion. So we'll just go straight through here. So that's our negative charge going straight through. Let's just write some kind of text to explain what's happening. So particle will continue in this diagonal, and I guess we want to stress that it's a straight line motion. Straight line motion, as there is no net force, and according to Newton's first law and according to Newton's first law, it is continuing on its original motion. Okay, and so that's how you would do that question there. It's a little bit of a tricky one, but you just need to understand that once the magnetic field is no longer exposed onto the negative particle, then the only way it can move is to continually go in that diagonal shape there, instead of this kind of parabola shape down like so. Okay, so if you found this video useful in explaining these kind of questions, solving for making proofs based on scientific data, or making analytical sense logic of how particles move in and outside of magnetic fields, give this video a like and subscribe, and I'll see you next time.